So I'm very pleased to introduce to you our next speaker. Dr. Norbert Pelc began his research in CT in the mid-1970s. And after graduate school, he worked on CT and other modalities at General Electric Medical Systems and later joined the radiology faculty at Stanford University. He's a member of the National Academy of Engineering and the National Academy of Inventors and was granted an honorary Doctor of Medicine by the Friedrich Alexander University of Erlangen-Nuremberg. He's a fellow of the AAPM, the ISMRM, the SPIE, the AHA, and the AIMBE. His awards include the Outstanding Researcher Award from the RSNA and the Edith H. Quimby Award from the AAPM. And I look forward to hearing his presentation. Norbert.
Thank you, Cynthia, for the invitation to come here and speak today, and the opportunity to see so many good friends. As we've heard, the first CT scan was done in the UK in 1971, October of 71, and the first CT scan in the United States was done here 50 years ago. This talk will cover some stories. I'm not going to go into technology in detail, rather try to tell some of the stories behind the developments. There was a lot of early research related to CT. We often nowadays start the description of the technical aspects of CT with radon and work that was done in mathematics in the early part of the 20th century. There was also work done in electron microscopy and radio astronomy. Later on, we learned that there was research done in Kyiv in the 1950s on X-ray CT. But the people who contributed to the story that developed the scanner that we're commemorating today really didn't know any of those stories or that technology. So we will start our story today with Allan Cormack. I want to acknowledge the many sources of information and a few things that you could look at if you want to read a little bit more about this. I want to give much of the material comes from two papers that you see listed on the bottom. And I want to give special thanks to the co-authors that contributed to those two papers, Raymond Schultz, who's here in the audience, Jay Stein and David Chesler. And then also listed, you see a number of people who have shared their memories and materials with me for this talk, contributed to those papers as well. So we will start our story with Allan Cormack, as I said, and then we'll talk about very early work that was done at Siemens before the development of the first of the EMI scanner, before introduction of the EMI scanner, I should say. And as we do that, I want to talk about the mindset of people developing technology and using technology and radiological imaging back in that day, because that affects some of the things that happened. We will then talk about early CT-related work at MIT and Mass General Hospital before the first use of the EMI scanner, and then talk about Hounsfield and the development of the scanner that was eventually deployed here. We'll then talk about other market entrants and what happened in the radiological field, especially on the commercial side, but not entirely commercial, in the period of rapid innovation. Competition, cost containment, you heard a little bit about that, and market consolidation we'll talk, and then some closing comments. Allan Cormack was a South African physicist who worked part-time in radiation therapy. And when he thought about how would one go about doing accurate treatment planning, he realized that what we needed was three-dimensional maps of linear attenuation coefficient. And so the thought came to his mind of how would one produce such images from measurements of transmission made externally, and that you needed to reconstruct a function from those measurements. And he did some literature search and did not find radon, and didn't find anything on how one would reconstruct this. This was in the early 1960s. So he did that literature search, was surprised to not find a solution. So he came up with his own and then proved that it worked by making measurements of a phantom with a cobalt-60 source and reconstructing the attenuation coefficient distribution of that phantom. He then approached the physicists at his hospital and told them about this, and to no avail. Nobody was very interested in this. The story that I wanted to tell you about Siemens is told in that paper that you see listed on the bottom by Walt Robb. An R&D team at Siemens in the 1960s realized, led by Professor Gooden, realized that they could reconstruct a map of linear attenuation coefficients from external measurements. The radiology field at the time was really focused on improving spatial resolution. Feeling was the way that radiology would be better is if the images could be sharper. That extra detail would allow them to see the unseen things. And so that was the mindset. And so the scientists at Siemens felt that the technique could only be useful if they could match the spatial resolution of radiography. So say on the order of 150 micron resolution. And when they looked at computer technology that was available and how it might progress, they concluded that sufficient computer technology wouldn't be available for decades. So the project was stopped. Nothing was published, as far as I know, or patented. At least I couldn't find any. By this time, Hounsfield was already well underway with developing the prototype scanner. I want to talk about a couple of other people who were working in the CT area that before the first demonstration of the EMI scanner. One is Oleh Tretiak. He trained as an electrical engineer at MIT and then joined the faculty there. And then in the 1960s, worked at MIT on image processing and image recognition with interest in biomedical imaging. He independently derived reconstruction by Fourier interpolation. He actually independently, as far as I can tell, independently derived what we now call the projection slice theorem or the central slice theorem. And he made cross-sectional images of an excised bone from scanned radiographs of that bone on a turntable as the turntable was moved. He went to one of his colleagues in the EE department at MIT and told them about this. And as it turned out, that person had just read a paper on electron microscopy reconstruction from projections. The paper would have been the Desrosiers and Klug paper. And so Tretiak felt scooped because someone else had just demonstrated this reconstruction by Fourier interpolation. It makes you wonder what might have happened if he realized that the images that he had produced were one of the first CT reconstructions of linear attenuation coefficients made by projection measurement. He didn't know that Cormack had already done that as well. David Chesler is a mentor of mine and also Steve Riederer's. Dave Chesler also came out of the MIT EE program and worked in industry and joined Mass General Hospital in the late 1960s because he didn't want to work in the defense industry. He instead worked in nuclear medicine and independently derived filtered back projection reconstruction with his interest being for the use of that reconstruction in emission tomography with single photons and positron imaging, which had been developed in that laboratory at Mass General Hospital. However, in the process of producing these images, he wanted to do attenuation correction. So for attenuation correction of those images, he also acquired transmission measurements and reconstructed images of linear attenuation coefficients. Those would have been very, very noisy, but nonetheless, they probably were some of the very earliest reconstructions of linear attenuation coefficients. That said, clearly after Cormack, Hounsfield, and Tretiak, because Hounsfield had by then produced images in his laboratory. Those results were presented in 1972. So now let's talk about the story of Hounsfield. Some of this you saw in the movie. He trained and got an associate's certificate. That's the extent of his formal training. He, during World War II, worked on radar and then joined EMI and worked on a variety of topics, including radar system, displays, general purpose computers, and pattern recognition. And as you saw in the movie also, in the 1960s, he was pondering various things, and he asked himself, could he recognize text in a closed book by making external measurements, or could he discern what's inside the box from measurements made readings through the box? And you saw that told in the movie. On a holiday, as they would say, rather than on vacation, on this holiday, he met a physician who bemoaned the drawbacks of radiography and the difficulties in seeing things in radiography because of superposition. And so Hounsfield realized that that is an example of his what's unknown thing in the box. How do you reconstruct what's inside the box from measurements made from the outside? So he started working on that a little bit more. And he considered the problem of 9 unknown numbers or unknown numbers in a 3x3 box. Could he come up with a method of reconstructing the contents of those 9 cells from measurements made at 0, 45, 90, and 135 degrees? And he came up with what we would now call the algebraic reconstruction technique. He then worked with a colleague. He wasn't apparently much of a programmer, neither was Cormack, by the way. And he worked with a colleague who programmed that and was able to produce images of an 8x8 matrix from a version of that. In 1968, he approached EMI for funding for the idea of making a medical scanner using this principle. And EMI decided that they would not allocate internal funds until he got substantial funding from the UK government. And so he applied for funding from the Department of Health and Social Services in the UK. And we're all familiar with this. His grant application was rejected. So he resubmitted that grant application in October of 68, I'm sorry. And you know, it's great that some people preserve these things because we still have copies of that grant application. And you saw some images from that grant application in the movie as well. It was called an improved form of X-radiography. And in the introduction of that grant proposal, you see the text that I outlined here. If the object to be studied was one such as a book, normal methods of X-ray pictures. So you see the connection between the grant application and the problem that he was trying to solve of discerning what's inside of a box from measurements made from the outside. So in that, and this, the image on your left, you also saw in the movie, which is one of the figures from that grant application that shows the idea of an X-ray source and detector that would scan across the patient and then rotate and make measurements one slice at a time. But on the right, you see another figure from that 1968 grant application that shows cone beam CT with a 2D detector. So in that same grant application, he described what he foresaw as the potential benefits of this technology: high dose efficiency, sensitivity to minute changes in attenuation, lack of superposition, and envisioned a possible role in the detection of cancer. He also foresaw that we would need some way of displaying these images, which would have a very wide dynamic range, much wider than any medical image at the time. This is how window level idea came into radiology. It was not available before that because there had been no need for it, or at least no recognized need. In the grant application, he discussed a variety of technical topics like sources, detectors, scatter and beam hardening, and the relationship between scan time and various system design choices to achieve his goal of this 1% of the attenuation coefficient of water resolution in density. So the grant was approved, and the combined funding, this combined funding from EMI and the UK government was £69,000. And that led within a fairly short time to the first CT scan of a patient in about 3 years. And as you saw, about a little more than a year later, the first CT scan here in the United States at Mayo Clinic. The first scanner that he produced was called the Lathe-bed scanner, and it had a radioisotope source rather than an X-ray source. So the scan time with this machine was 9 days to get sufficient photons. So that the americium source was replaced with an X-ray tube, and the scan time came down to 9 hours. And they required at the time 2.5 hours of CPU time on a mainframe to produce a 32 by 32 image. They scanned brain specimens and a variety of other things like the pig carcass that you see there. Ambrose, who was a neuroradiologist who was working with Ambrose and providing with Hounsfield and providing advice, even with these very crude images, recognized the potential that they would have and said to Hounsfield, "Do you realize what you have done?" So in January of 1970, EMI decided to produce and build a prototype. While this was happening, Hounsfield visited a number of radiologists and told them what they were trying to do at EMI, and in general got a very cool response. And I think in large part it was because of the spatial resolution, which was going to be on the order of 3 millimeters, far, far poorer than radiography. Plus, this machine would require computers, which were not being used to any extent in radiology. The machine would be expensive. And in general, I would say that they didn't realize what the impact would be of the far improvement in density resolution that would be gained by this and the removal of the superimposition. Nonetheless, by August of 1970, the specifications for the scanner were complete. The machine, you see the photograph you see there is the EMI Mark I, which was that first prototype that was installed at Atkinson Morley Hospital in Wimbledon, London. It had a water bag. The patient's head was in a water bag, and the water bag was filled with water. That had a number of technical benefits. And as you saw in the movie, it produced 2 slices in a single scan of about 5 minutes, used a fixed anode X-ray source, and the detector was 2 sodium iodide crystals, each with its own photomultiplier. So it was a 2-slice scanner, even though we then didn't call them multi-slice or multi-detector row. Didn't have multiple rows, just multiple. I don't know. Can you have a row of 1? Maybe. The raw data matrix was 160 samples and 160 views. They were written on magnetic tape. The magnetic tape was then taken back to the EMI central lab, where they were reconstructed on the EMI mainframe. And 80 by 80 images were printed on Polaroid film and returned about 2 days later. As I mentioned, the first scan was performed in October 1st, 1971. And the image you've seen before, it's often displayed of a patient with a cystic astrocytoma. Ambrose recalls that he and Hounsfield jumped up and down like football players who had just scored the winning goal with the success of that initial scan. There was an initial presentation of the results from the EMI scanner at the British Institute of Radiology conference in April of '72. And also, as you heard in the movie, there was then a presentation at a neuroradiology postgraduate course in New York City in May of 1972 that generated huge excitement because the leaders in neuroradiology in the United States were there. And they quickly appreciated the potential that these images presented. Among the things that were retained, and actually when I was speaking with Steve last night, I recalled reading this particular quote that I inserted in the talk last night, specifically for this audience. But there were notes that were taken and memos that were written by the EMI people of the reaction at this course in New York, and also some visits to potential customers in the United States that Hounsfield and some of the EMI people performed immediately after that course. So here's one EMI manager noted that hospitals like Mayo Clinic expect to examine 30 patients daily. The Mayo Clinic will examine as many patients in 1 week as had been examined by Atkinson Morley Hospital in Wimbledon during a whole year. It's almost correct, right? It's certainly within a factor of 2. Mayo Clinic was mentioned in those early internal memos by EMI people. So shortly after that, the EMI scanner was shown at the RSNA in 1972. There was no planned scientific presentation at the time because all of this happened too late for the submission deadlines. And I think it's fair to say that EMI as a corporate entity didn't appreciate the importance of the RSNA and what could happen as a result. But they learned of that, and they had an exhibit in 1972. And Ambrose and Hounsfield were able to speak immediately after the president's address at the RSNA meeting that year. And it proved to be a huge success. And major US hospitals started to order machines. And what we learned is the Mayo Clinic essentially bypassed that. There's a serendipity that I think is worth noting. EMI's initial estimate of the market for CT scanners was 12 machines worldwide. And part of this was that the model of reconstructing images on a mainframe and returning them was just really not viable. And what enabled CT to become a reality and to be distributed so quickly to so many places was the development of the minicomputer. So just before this was going on in the mid-1960s, minicomputers started being introduced. And by the time they were needed for CT scanning, we had availability of sufficiently powerful minicomputers at reasonable price. And they got incorporated into the scanners, and the reconstructions could happen locally, and the data wouldn't have to be sent. And so here you see a photograph of EMI's scanner. I believe this was at the RSNA exhibit in 1972. And over here on the right, you see the Data General Nova minicomputer that was the brain's computational system behind it. So what was the industry reaction? I mentioned this paper by Walt Robb on his recollections of the first 10 years of the CT industry. And so he was there at the time. He was the head of GE Medical Systems as this was happening. And he said most manufacturers of radiographic equipment concluded that this new scanner would be a niche product, that it wouldn't greatly affect the field. And this was in part because of the long scan time, 4.5 minutes, and the modest spatial resolution that was achievable at the time. Siemens, as you recall, Siemens had looked at this idea and, in a sense, set it aside, Professor Gooden, who was who had led that team at Siemens, was astounded by the fact that these images, which were proving to be so powerful, only had an 80 by 80 matrix, about a 30th in each dimension compared to what they thought would be needed. And then this is also from Walt Rob's paper. One member of the team confessed, "It took us months to comprehend the significance of density resolution versus spatial resolution, and how we had been misled by being too closely associated with the conventional X-ray business." And I think that is really very perceptive. And you note that the idea of CT and achieving direct measurement of linear attenuation coefficients in this 3D way came from outside the medical imaging field, by people who were not tainted by this bias of. So at Siemens, the internal project, as you may not be surprised, was reinitiated, and Siemens embarked on the development of a CT scanner. I want to digress a little bit and talk about a story that pertains to my own experience and also Steve Riederer. I mentioned David Chesler, who was at Mass General and had developed reconstruction algorithms for nuclear medicine. The head of the laboratory was Gordon Brownell, who was a pioneer in what eventually got called positron emission tomography. And that was really the main activity of the Physics Research Lab at MGH at the time. But in mid-1972, I want you to think about when that is. Mid-1972, there is no CT scanner in the United States. We're still a year away from installation of the scanner here. The only scanner that had been made was the one that was in London. And the only public presentations were at most a handful, including the one in New York. But Gordon Brownell decides that the laboratory, which was really fully involved in positron imaging, would develop a whole body X-ray CT scanner. They started on that project. Dave Chesler was the lead person. And eventually a grant application was submitted to the National Cancer Institute to develop a whole body scanner. The submission was in 1973, and the grant was funded in November of 1973, roughly at the time that the first scanner was installed at MGH. But by then, the concept for this body scanner had already been developed. And this is an artist's rendering of what the scanner was going to look like. It was a third generation scanner, rotating fan beam, 10-second scan time so that it could do body imaging. The detector was a 256 element xenon ionization chamber, aligned with quarter offset, rebinning to parallel rays. These are all things that we're familiar with nowadays. One unique thing about this scanner is the channels in the detector array were unequally spaced so that when rebinned to parallel rays, they were equally spaced, and you didn't need interpolation in the radial direction in the reconstruction. So both Steve and I were involved with this research. Another activity by the NIH was in 1974, the NIH issued an RFP, a request for proposals, for development of whole body CT scanners. There was a competition for this. It was won by Columbia Presbyterian Medical Center and the Neurological Institute of New York, where the PI was Sadek Hillel. And Raymond Schultz was involved in that program. And they collaborated with two subcontractors, including American Science and Engineering, which was based in Cambridge, Massachusetts. In general, I would say the federal investment in this early CT work was impactful, not just for the research that was done directly by it, but for the atmosphere that it set, because the companies got involved and started investing in CT, in part because they wanted a piece of that action, right? And a number of companies submitted applications to this RFP, which, as I said, was won by this team with Sadek Hillel and American Science and Engineering. We'll come back to a piece of that story in a little bit. The commercial activity then begins in 1974, right after the introduction of the EMI scanner the year before. Siemens and Hitachi introduced first generation head-only CT scanners. The same year, Robert Ledley, who was at Georgetown, founded a company he called Disco, and they developed a body scanner, which was essentially a scaled up version of the EMI head scanner. 5-minute scan time, first generation translate rotate. Very few of these were sold. In 1975, EMI introduced the 1010, which was a second generation. And those of you in the field know that in second generation, we have multiple detectors scanning and rotating, making the scanner faster. So it was eight detectors, and the scan time was reduced to 1 minute, and it also had no water bag. The same year, Ohio Nuclear introduced the Delta 50 head-only scanner and the Delta 25 and the Delta 50 body scanner. Neuroscan, which very few have heard of, developed a head-only second-generation scanner. I know of it because GE was marketing that scanner. I don't think they sold any. Syntex, maybe this was the first drug company that got into medical imaging. They were followed by a number of other drug companies later that got into the medical imaging market, introduced a head-only scanner. And the same year, the EMI 5005 that I think you heard talked about by Dr. Sheedy was introduced. And it had a second generation scanner with the 10-degree detector arc and could scan in 20 seconds. If you think about the idea of this mechanical gantry, scanning and rotating and scanning and rotating and being done within 20 seconds, that's pretty much as fast as you could get a translate rotate scanner to go. The quest for speed was on, though, because people realized we needed faster machines to scan outside of the skull. The concept of third generation scanning is often credited to Doug Boyd, but it seems to have been in the air. As I mentioned, Dave Chesler had come up with the same idea, as had Hounsfield. The scanners were built for speed, but the first two third generation scanners that were built were not for body imaging. The first one, is you see here, it was the GECTM. It was a breast scanner. And the first scanner was installed here at the Mayo Clinic. I mentioned relevant to what Dr. Sheedy talked about of people putting things in the head scanner. It was motivated by somebody at Mayo. I don't recall the name, but there are publications to this effect, putting mastectomy specimens in the head scanner to get a feeling for what breast tissue would look like. And you see there in the photograph, Red Reddington and Lonnie Edelheit, some of you might know. The same year, Artronics introduced a head-only third generation scanner. Later that year, GE introduced the body scanner with faster scan time. Artronics introduced a body scanner. Varian introduced a body scanner. You see a photograph of it there. And it was unique in a number of ways, including the fact that it had a slip ring and had continuous rotation at only 3 seconds. And all of these were third generation scanners with xenon ionization chambers. This detector technology is one that physicists trusted for stability and linearity. Siemens was bucking that trend. Siemens produced the first scintillator photodiode detector in a machine that was called the Somatome. And in that machine, they had another interesting idea. You see here in the bottom left insert, it had 2 detector arrays, one for the head and one for the body, that shared the same electronics. So you could put your 256 elements in different size field of views. Philips did this in a different way by having variable magnification in a third generation scanner that could change the location of the source and detector. All the third generation scanners at the time produced ring artifacts. You see examples of that there because of the stringent requirements on detector performance. J. Stein, who was at American Science and Engineering, recognized this problem and knew detectors well enough that he was very much afraid of trying to beat that requirement. And he came up with the idea of fourth generation scanners in order to avoid ring artifacts. And this was part of that program that was headed by Sadek Hillel. They produced the AS&D scanner in 1976 that had a 5-second scan time. And in my recollection, it produced the very best body images at the time. It also had post-patient collimation on each of its 600 detectors so as to be able to achieve higher spatial resolution at the cost of dose efficiency. The fourth generation design was later adopted by 2 other vendors, Technicare and Picker. EMI came up with a hybrid version of fourth generation scanner. They wanted the source to be on the outside of the ring. And so the ring of detectors had to nutate and get out of the way when the X-ray beam was penetrating through that. But the most strange machine was a fourth generation scanner by Artronics, and they liked gas detectors. So now try to come up with an idea of a gas detector that has internal collimation and the cells are very directional. How do you put that together with a fourth generation design? The source has to be in the center of a ring of detectors, which you see here, but then the patient can't be in the center. So here you see the patient off to one side, and then the entire thing rotates about the patient as the source rotates within the center of the circle. I remember seeing this machine at the RSNA and just was astounded. And there was a movie of it. So here's the ring of xenon ionization chambers. The source is here. The source is going to rotate around this as the circle wobbles about the patient opening. Very ingenious, I thought. And it's a slip ring scanner. It could keep doing this all day long. I don't think more than a handful of these were sold. Okay, I can't advance that. Good. Some other technology that was developed at around the same time, the Electron Beam CT scanner came out of UCSF, an academic center, and then was later commercialized by Imatron, targeted at cardiac imaging and recognizing the need for imaging multiple slices with very short scan time. And of course, we have the work that was done here on the dynamic spatial reconstructor. You see a photograph there and a drawing of it. It had multiple X-ray sources. It was inherently a 3D volumetric scanner and could produce snapshot images of the heart. You see examples of that here from a paper that came out of the group here at the Mayo Clinic. Really quite visionary in many ways because inherent in this view of what CT of the heart should be was an understanding that it had to be 3-dimensional, it had to have very high spatial resolution, and you needed to have the ability to reformat it to the different planes at which you would want to view the cardiovascular system. So getting back to the competition, GE had received advice to drop third-generation design because of ring artifacts and the pressure that was being put on the market by the AS&E scanner. But they resisted that, were able to solve the ring artifact problem, and then developed a higher resolution scanner that was called the 8800. Other third-generation companies soon followed, and this put tremendous pressure on the fourth-generation scanners because they had an inherent cost disadvantage and other dose inefficiency and scatter problems. So third-generation scanners began to dominate the market. At about the same time, and you heard from Dr. Sheedy and Dr. Forbes, the government imposed cost constraints And this had an impact, as did the introduction of MRI. And here you see CT scales over time, and you see a peak, and then the introduction of certificate of need, and the size of the CT market drops. It then recovers, and then it's hit again by further government regulations, as well as the introduction of MR. This was especially hard, this reduction in market size, on the small companies, and the small companies began to drop out. So early on, this innovation came from not only outside the medical imaging field, but certainly outside of the major radiology companies. But by the early 1980s, all of those market entrants had disappeared, and the CT market was dominated by the traditional medical imaging companies. In '79, the Nobel Prize is given to Cormack and Hounsfield for the development of CT. And in the award, it said, "It's no exaggeration to state that no other method within X-ray diagnostics within such a short period of time has led such remarkable advances in research in a multitude of applications." Some closing thoughts. Before CT, as you heard, X-ray imaging was focused on improving spatial resolution. There was a bias against accepting any lower spatial resolution, even if it obtained true 3D images, very good density resolution. This innovation came from outsiders. Only now we're approaching the spatial resolution that Siemens thought would be necessary. We're getting there. Government funding for this research and development was really instrumental, but then government intervention in the market was disruptive and perhaps negatively so. The introduction of CT brought computers into radiological imaging. I don't know if we're happy about that or not. And the success of CT paved the way for other innovations, including magnetic resonance imaging. Thank you.